Okay, this is going to be a slightly confused talk because it's something I've thrown together over the last couple of hours, but it's basically about my adventures over the last few days in trying to put together a brain for 3D printing. So I work a lot in MRI scanners, and sometimes it's really useful to have a model of a brain that we can scan rather than having to find someone who's actually willing to go and scan it for us. So just to start, we've got a couple of imports of a few useful libraries. So the first thing we're going to do is read in a file which contains just a standard brain. This is called the MNI152, which is just actually the average of 152 different people's brains, so that we get something that is not perturbed by the vagaries of any individual person. And so that looks something like this. You can see it's a bit blurry because we're averaging a lot of things together. Again, matplotlib, we're showing just pulling out one individual slice from the middle. Now the first thing that we need to do to extract the brain is remove the skull and the rest of the tissue from outside. And we can do this with a really nice tool called the Brain Extraction Tool, or BET. And this is available from the FSL library from NiPipe, which is a collection of tools for messing around with digital brains. So you see we can create this BET file, pass in the name of the file that we want to run, and then give an output to produce this brain file, which we then read back in. And to plot this, you can see now that our brain, compared to the original, this is the whole head, and now in this case we've lost the skull. All the rest of the things, we're just left with the brain. So the next thing that we need to do is to separate the brain into the different tissue types. So inside the brain we've got white matter, and we've got grey matter, and we've also got the cerebrospinal fluid which surrounds it. And in order to get a good model, we need to divide this into the different regions so that we can have kind of hard lines that separate out these different tissue types. So again, we can use another tool from the FSL library, which is called FAST. And when we run this, you can see we separate out the tissue into these distinctive labels. So we have obviously the space around, and then the CSF, the grey matter, and the white matter progressively going inside. Now this is great, we've got our individual regions, but what we now really want to do is to separate this out, or extract the contours that define the boundary lines between all of the different regions, so that we can print the solid walls but keep the spaces in between hollow. So the way we can do this is by using the measure library from scikit-image. And so here there's this very handy function, find contours, where we pass in different labels. So in our map we have different regions 0, 1, 2, and 3 for the different regions that we have. So if we pass in halfway between all of those regions, then we collect these different contours, and I'm just gathering them together. And you can see now, if we plot the contours on top of the image, that we've extracted these boundary lines between the different regions. So the next thing that we have to do, of course, is to turn this into a 3D model. So at the moment we have individual line segments which go from point A to point B all the way around the regions that we care about. But to have a 3D print, we need to have a solid region rather than just a line that's going along. So the way that we can do this is with a sweep type option. So at each individual point between lines, we can create a rectangle that is perpendicular to the path that we're following, and then we can create a tube which connects together all the different rectangles that go around. So what I have here is a function which will create this path from the contour. So for each point, as we go around in a particular contour, we go along each line segment, and at each point we work out the direction that the path is pointing in. And in this case, because of the way that Scikit outputs the things, we're also just skipping. So every time that we find two segments which are pointing in the same direction, we combine them into a single section. But then we just output these pairs of a point and then the direction in which it's going to the next point. And then the library that I'm using to create the actual image itself is OpenSCAD, which, if you haven't heard of, is not a Python toolbox, but a similar language format which is used for describing 3D geometry. And so what I'm doing here is outputting OpenSCAD code. So we take in the path that we've just created and generate these individual rectangles, which we can do by passing the things along. And so when we run this, we get something, that's the wrong way, which looks like this. And then after a few hours in the 3D printer,